So it just happened that 1825 here in Budapest, in Hungary, that that was the period which we called just the reform age in the Hungarian history, when many noble people realized that the agriculture-based, feudalistic, society is not the future, and they wanted to make some changes. And on this picture, what you have seen, this is actually on the wall of this building. One of them in the parliament stand up, Széchenyi, and he just gave 1 year of his income to fund the Hungarian Academy. And on this figure you could see that there are others who are also joining him to do that. So that was an event when the Academy started here. And the Academy first focused on protecting the Hungarian language, cultivate that, and also mainly on literature, but later on they were also starting to support science as well. So the building where we are sitting now was built in 1865, next to the Danube. And what is interesting that at that time the Academy was so famous and had such a large reputation in Hungary that it was also built up from donations, and not just from rich noble peoples, but also middle class people give quite some money to set this building up, and they also set the capital for the Academy to run its activities. So this was 200 years ago, and of course 100 years ago there was another important event happened. There is another logo on the left corner, which is the foundation of quantum physics, which happened around 1925. That was the time when the first proper model of the hydrogen atom was invented. Schrödinger wave function with wave function formalism, and also Bohr and Heisenberg, they were working on a matrix formalism. And so this happened 100 years ago. I guess many of you were in different events related to that. And most of that story, on the German side with Bohr and Heisenberg, happened in Göttingen in Germany. And the two story, the Hungarian science and also the foundation of quantum mechanics met in Göttingen at that time. So there were some Hungarian contributors. Here I just have to say that, from this, in these 200 years, continuously Hungarian science improved. And in the beginning of the 20th century, actually Budapest became a quite vivid and multicultural city in Middle Europe. And also the education system was particularly strong in Hungary, especially math education, and there were some famous guys who born here, like János von Neumann, who he born and learned here in Budapest, and he loved mathematics already during his childhood. And but his father, he came from a rich Jewish family. His father saw that he should do something more serious than mathematics, so he also studied some chemistry studies, and he made a PhD from math and also from chemistry. And he got to Göttingen in 1925 because he had to do some teaching duties for his habilitations. And as a side project, he started to work with students of Hilbert at that time, who was also there. And he got to know this problem that there are two different descriptions of quantum mechanics, and we don't understand why it describes the same. So he spent there 1 year, and he made a trilogy of three papers. The title of the first one was, the Mathematische Begründung der Quantenmechanik, so the mathematic foundation of quantum mechanics. So he just made, serious mathematical derivation, that the two pictures are the same, and he described how one should properly handle that on the mathematical side. So that was a side project from him. After that, he went to the States, and I mean, he had important contributions in different fields of mathematics, like game theory. He also worked on the atomic bomb project, and I mean, as a side project, he just set it up, the architecture of modern computers, what we are using. So all of his, I mean, what was also famous from him when during the atomic project, you know, they were running some old computers at that time to make some calculations. He was so fast calculating in head that he was checking the computer by doing the calculation the same time in head to see whether it's working well. So due to, I mean, his lots of activities in science and mathematics, the Financial Times chose him the man of the last century. So he was there, and he, from his secondary school, from the same math teacher, there were another guy who got to Göttingen at that time. It was Jenő Wigner. He also came from a Jewish family, and he founded the group theory in quantum mechanics. Later on, I mean, here you can see a photo together with Heisenberg as they were working in Göttingen, and later on, he also went to the States. He also worked on the atomic bomb project, and became the founder of nuclear power plants. So that's the Hungarian. I mean, maybe I should mention another guy. He was also working together with Heisenberg, and he also came from Budapest, Ed Teller. I mean, he was the inventor of the hydrogen bomb later, and he had quite some contribution to molecular spectroscopy, like splittings of the spectrum of molecules. So these two stories get together, and after this historical background, I would just ask Ádám Gali, who is the head of the Quantum Informational National Lab, to come here and tell you a few words about what is this lab, and to open this conference. So Ádám, please.
Thank you for the invitation. My name is Ádám Gali, and I work at the Wiener Research Center for Physics and also in the Budapest University of Technology and Economics. I'm delighted to be here, and welcome to Budapest. So thank you for all of you coming here and celebrating the bicentennial foundation of the Hungarian Academy of Sciences. And previously, we had some understanding about the past, how Hungarian physicists or scientists contributed to the field of quantum mechanics. But also, I would like to mention here that we just funded, with the help of the government, this Quantum Information National Laboratory in order to gather all the research groups that are working in this field and try to make a so-called critical mass that we are possible to show up that we have here present working on quantum mechanics now in the second revolution of quantum mechanics, and now we're working on to coherently control quantum systems, both in the laboratories founded in these research programs I'm showing there, and also a theory in order to use quantum information science to test new hardwares, quantum computation hardwares. So in particular, this Quantum Information National Lab encompasses all the physicists, engineers, and mathematicians working in Budapest in 3 institutions with altogether 4 faculties, plus the Wigner Research Center for Physics. So what we hope that with this conference you can find and you can meet with the scientists from Hungary, and we hope that we will have also a significant contribution to to the physics in this field. And with using your knowledge, global knowledge, you know, when you come from, let's say, Australia or Netherlands or the United States, we will learn how to organize ourselves to be able also to harness the fruits of this quantum science to make technologies and also contribute to and make it beneficial for the entire society. With this, I would like to thank for your coming, and I hope you will enjoy to be here in this nice city. We are lucky with the weather, so I hope it will stay for the boat trips, and I hope that you will also enjoy the scientific part of the conference, and I trust it will be a very high level because of you. Thank you again. Thank you very much.
Good, and time is running, so I will just skip now the organization details, since anyway not all of you are here. So there are 4 workshops are running parallel in this conference, and 2 of those will just start tomorrow. So I will leave this information for tomorrow to explain it to you. Then let's continue with the first plenary session, and I just ask Péter Domokos to come here and chair the session.
Good morning, everyone. So I greet you here at this plenary session. We are going to have 2 speakers. The first speaker is József Fortágh, and it's a great pleasure to introduce him, because he started his studies here in Budapest, then he was attracted and absorbed in the quantum world of Theodor Hensch in Munich. So he continued his research career there, and finally he earned his PhD at the University of Tübingen, working with Bose-Einstein condensates in microtraps. Then, spending some time at Stanford and Queensland University, he ended up in Tübingen, and he is now a full professor at the experimental physics department at the Tübingen University, where he has a research group working on atom chip-based ultra-cold atomic systems. And the specialty of his research is one of the specialties is the hybrid quantum system. So this is a very good combination here for this plenary session, that he works with atoms and also superconducting elements. So he has also important roles in the Hungarian scientific life. Beyond the informal collaborations, he also has a formal position. He was the chair of the advisory board of this Quantum Information National Laboratory. So we are looking forward to your talk, József. Thank you.
So, Peter, thank you very much. Good morning, everyone. It's very nice to see you here, and thank you for the opportunity to share with you our research on hybrid quantum systems combining cold atoms and superconductors. Now, before starting let me take you on a short journey around this very place here around. You can see here the city of Pest in the 19th century, just a few decades after the foundation of the Hungarian Academy of Sciences. We recognize the buildings as today, the familiar street layout, navigation on the Danube, and if we turn to the Buda side, we see steamships and bridges being built. So this was a time of great progress in society, science, technology, and infrastructure. Now let's take a leap further, jump to the future, and picture the infrastructure we may find there. Imagine quantum technology in everyday life. Quantum computers are optimizing economical and logistical tasks. Quantum simulators are assisting the design and synthesis of new materials. And quantum sensors deliver signals from early warning systems, all connected via a fiber network to form a quantum network that supports decision making. Now, these quantum computers, quantum simulators, and quantum sensors operate on very different platforms. Some on superconducting circuits, some on color centers, other on atoms and ions. Now, atoms, ions, and color centers can be directly connected to such an optical network by emitting quantum light into the fibers in the telecom band. Connecting superconductors is more challenging since superconducting circuits operate in the microwave domain. A bridge could be built by atoms that interact with both microwave and optical photons. Superconducting circuits are usually connected to microwave cavities that is illustrated here as a box. The microwave cavity confines the photons for some time, which is again giving us the time to transfer the quantum state to atoms. The atoms can transfer the quantum state further via Raman process into the optical domain, and the emitted light can be collected using a cavity that is formed by a mirror and a fiber tip into the network. This concept may enable superconductors or superconducting quantum computers to participate in the quantum network. There is a landmark experiment by Dave Schuster and John Simon on microwave to optical conversion, essentially millimeter wave to optical conversion in a box at 4 Kelvin, essentially very similar to this diagram. Now, further challenge is integration into a compact device and moving from 4 Kelvin to millikelvin temperatures where superconducting circuits normally operate. So this is the challenge that we address in our research step by step. First, integrating atoms with superconducting chips, and then moving to millikelvin systems. The idea is summarized on this image. Here, a superconducting circuit, atoms, and an optical fiber cavity form a hybrid quantum system. Our consortium that is funded within the Quantera call involves researchers from Bordeaux, Budapest, Heraklion, Turin, and Tübingen. Our task in Tübingen is to interface the atoms with superconductors. Now, let me take you into my laboratory for a short moment. On the optical table, you can see a laser system, and back behind, I'm preparing the vacuum chamber for the experiments. Here behind the curtain, some colleagues are testing a new single atom detector that I'm going to introduce some later. Here, once the lasers are aligned, adjusted, we collect atoms in a magneto-optical trap that then we further transfer them to atom chips on which our experiments take place. Now we can enjoy a bit the laser light in the laboratory and now see the magneto-optical trap in the vacuum chamber just with naked eyes. Atom chips are versatile tools to manipulate ultra-cold atoms. Tiny conductors on chip surfaces driven with electric currents generate magnetic trap above the chip surface. By changing the currents, we can move the atomic cloud closer to the surface, further away, or translate the atom along such a chip. Even Bose-Einstein condensates can be manipulated like this. The basic principle is the wire trap. This is essentially the simplest trap. By Biot-Savart law, a current-carrying wire generates a tangential magnetic field which decays with the distance from the wire. By adding an offset field from the side, a magnetic quadrupole is formed at the wire in which paramagnetic atoms can be trapped. Our workhorse atom is rubidium. It has one electron on an S shell and a nuclear moment, thus the ground state is split into two hyperfine states with a total spin 1 and 2. Only low field Zeeking states are trapped in a magnetic trap that are marked with the dot. We usually trap the F=1, -1, or the F=2, +2 quantum states. We see the equipotential lines of the magnetic field, and we observe on this image on a thermal cloud or a Bose-Einstein condensate that gravity is shifting the atomic cloud a bit off from the magnetic center. Now, going back to the atom chip I've shown before, I illustrate you how we translate atoms by changing the currents in the conductor. So the atomic cloud is loaded, translated to some specific structure on the chip surface that can be functionalized, or the atomic cloud is split for further experiments. The properties of the atomic cloud are summarized on the next slide. We trap up to 1 million rubidium atoms at temperatures down to 100 nanokelvin at a few micron separation to the chip surface. Under such experimental conditions, we can observe interactions between the atoms and the solid, such that Casimir-Polder interactions between atoms and the surface, where atoms are sensing electromagnetic fluctuations generated by the surface. Exactly these interactions motivate the development of solid-state hybrid quantum systems where we link atoms and solids on purpose. One of the early vision of a hybrid system is the hybrid quantum processor. So let's look at this. So the information is fast processed by a superconducting qubit. The result is transferred with microwaves as a data bus, with a microwave cavity as data bus, to the cold atom quantum memory. And the state can be further transferred to optical photons. The microwave to optical conversion from the circuit can be achieved using Rydberg atoms. So by phase-matched pump lasers, the emitted light can be directed to a fiber tip even without an optical cavity, which simplifies an integrated device. From the fundamental point of view, Rydberg atoms strongly coupled to a microcavity represent a quantum spin system with not only next neighbor, but long-range all-to-all interaction, and it's a test bed for fundamental physics. It should also work, actually, with cavities in a thermal state. So these fundamental and technological potentials motivated us to set up two experimental systems interfacing cold atoms with superconductors. To the left, a cold atom setup integrating a 4 Kelvin helium flow cryostat, and to the right, a dilution fridge in which we integrate a cold atom setup. Let's start with the left. The laboratory looks very similar to the other in the movie. If we take the view of this CCD camera into the vacuum chamber, we can follow the cold atom preparation. To the right, room temperature electromagnets in the vacuum. To the left, the helium flow cryostat with a 4 Kelvin cold chip surface and a cryo shield at about 20 Kelvin. We prepare about 100 million rubidium atoms using a magneto-optical trap. The atoms are then loaded into the strongly confining magnetic trap for evaporative cooling. After evaporative cooling, about 2 microkelvin cold cloud containing a few million atoms is trapped by optical tweezers and translated below the superconducting chip where magnetic fields take over the trapping. The chip has some niobium wire components for magnetic trapping and microwave cavities on the surface. Now, for fun, we integrated a superconducting ring to the chip surface. You know, experimental physicist likes playing in the laboratory, like adjusting the lasers, like to try things that you would never think about. This you may think about what is the ring good for. If we cool down the ring, then it traps magnetic flux. With a ring radius of 10 microns, 67 milligauss applied field before going through the superconducting transition temperature corresponds to exactly 1 flux quantum. This can be sensed by a Bose-Einstein condensate. In the experiment, the field of the ring adds to the field of the magnetic trap and deforms it. We measure the number of atoms in this dimple as a function of the applied field to the ring, and we see steps in the atom number. So this is a direct atomic probe of the flux quantization. Now I move back to the main track and look at the cavity. Persistent currents, like on the ring, can be used also to form stable magnetic traps on the chip that we formed on a cavity. It's a closed loop structure that is able to confine atoms just above the cavity when a bias field is applied. In such traps, the atomic cloud has a long lifetime. We can store an atomic cloud for several minutes, and we can generate Bose-Einstein condensates in both of the hyperfine ground state 1 or 2. The coherence of superposition states we measure in a Ramsey type experiment employing a pi over 2 pulse, and after some variable waiting time, a second pi over 2 pulse, and testing the atom in the lower or the atoms in the lower or the upper hyperfine state. And we observe a coherence lasting for several seconds. So the status at this point, we have atomic clouds at the superconducting chip. We have long lifetime, long coherence of superposition states. So what is about atom cavity coupling? Our fabricated cavity is a niobium structure on sapphire and matching the transition frequency of the rubidium ground states from F equal 2 to F equal 1 to F equal 2, 6.8 gigahertz. This fabricated cavity compromised because we have wire structures for magnetic trapping on the same chip is about 10,000. We can tune the cavity resonance by the temperature essentially fine-tuned to the atoms. Of course, the atoms can be also shifted using magnetic fields to match the cavity resonance. Now, at about 20 microns to the chip, the atomic cloud is positioned for the following experiments when we apply a strong microwave drive to the cavity to observe the transition between the both hyperfine states. So what we observe by driving the cavity is Rabi flopping, but the oscillation washes out on the time scale of an oscillation period. Now, look at this. The lower hyperfine state is trapped magnetically. The upper, that to which we coupled with a single microwave, is not trapped, so it may displace during the experiment. Of course, we can exclude this if we couple the lower state to if you couple a state pair which is equally trapped magnetically. This requires in the experiment an additional radio frequency field, but the result is the same. So the reason for the decay is the inhomogeneity of the driving field. Atoms close to the cavity oscillate faster than atoms further away. The cloud has a large extension. So in the average, in the ensemble average that our absorption image is taking, the signal just washes out. At the same time, I notice that the single atom coupling, if we couple the magnetic dipole of the atoms to the magnetic field of the cavity, is rather weak. So the strong coupling regime is here far out of reach. The question how to achieve that. One possibility is, of course, we have a large atomic ensemble of millions of atoms. So collective enhancement, which scales with the square root of the particle number, may help us at this point. Or we make a rather drastic step and change from the magnetic dipole coupling to a much, much stronger coupling, electric dipole coupling of highly excited Rydberg atoms to the microwave field. We have taken now first this second part. The first may be still interesting. So in order to excite Rydberg atoms close to the superconducting chip, we added a few more laser beams so to the setup. We have anyway many, so two more doesn't change too much. And now we can excite Rydberg states with a principal quantum number around 50. So in these experiments, we excite n equal 28, 27. And the state pair, Rydberg state pair R1 and R2, are resonant with the third harmonics of the cavity, now 3 times 6.8 gigahertz, about 20.5 gigahertz. For the experiments, we only excite single Rydberg atoms in the atomic cloud, and in order to be able to detect whether the atom is in R1 or R2, we developed a single atom detector, a state selective single detector based on field ionization and ion counting using a channel electron multiplier that you saw in the movie colleagues tested already earlier. So this is capable to tell us whether the atom is in R1 or R2. So before we start the experiments, I have to notice a challenge, which is due to deposition of atoms to the surface. Whenever we prepare an atomic cloud at such a tiny distance to the chip surface, tens of microns, with a cloud size of tens of microns, then we can't avoid that some of the atoms stick to the surface. Rubidium is an alkali. Once the atom is sticking to the surface, it is sharing the outermost electron with the surface and is polarized. So we have a strong electric dipole field at the chip surface, exactly at the position where we wish to perform the experiments. And on the long list of these citations, you recognize that this problem is not only bothering me, but all of our colleagues who are working with Rydberg atoms on chips. So in our experiments, to some extent, we can compensate this field. On the other hand, we have to take into account that Rydberg states are split, and we can still select a Stark split or Stark shifted state pair, R1 and R2, in this Stark manifold, which is matching the cavity resonance. The experiment is as follows. We excite the atoms by the lasers to Rydberg state R1. We apply a microwave pulse of variable length, after which we turn on the single atom detector, starting with the field ionization and watching whether the atom is in R1, arriving in R1 or R2, to observe state transition driven by the microwave here between the two Rydberg states. If we do so, we observe again Rabi flopping, which scales the Rabi frequency correctly with the driving power, but the decay is still there. So, although we excite in each experiment a single atom, we see the signal decaying. So the answer many of you know already, but I'm presenting here. The atomic cloud is positioned at some distance to the chip surface and has a large extension. Now, the surface adsorbate field helps us to select only a single layer in this atomic cloud in which atoms can be excited by the optical field. At this distance, the lasers are resonant. Neither below nor above the lasers are resonant because the dipole field of absorbates is shifting the atoms out of resonance. So we excite in every repetition of the experiment one Rydberg atom somewhere in this layer. But still, in the repetitions of the experiment, the Rydberg atoms are excited at different positions. And in order to record such a diagram, the averaging is again washing out the contrast. Nonetheless, we were able to increase the coupling by 3 orders of magnitude, and by selecting other Rydberg states, other Rydberg transitions, other dipole moments, we can further increase this, so it's an encouraging path. And these results now set the path forward. What we have to do, we have to use optical tweezers to localize Rydberg atoms in the cavity, that the Rydberg atom is always at the same point in the cavity when we perform the experiments. Second, we should leave the planar chip geometry behind. We could take a flipped chip geometry which provides a much more homogeneous cavity field, but also a much more homogenized stray field, so we get a better control. And at the same time, such a geometry is supporting strong coupling. As the diagram shows, we take flipped chips with lumped element cavities and capacitor plates in which the microwave is confined, with a plate capacitor separation around 100 to 200 microns that we can access with optical tweezers. The setup, strong coupling is feasible. So this is the path that we follow now in our experiments, and not only at 4 Kelvin, where the cavity still hosts some tens of thermal microwave photons, but also in a millikelvin setup, where the cavity is cooled that far that it is empty. of photons, and it's advantageous for quantum conversion of microwave into the optical domain. Now, the millikelvin setup is in a UHV, in a large UHV, ultra-high vacuum chamber. It has several cryoshields with optical axis for the laser manipulation of atoms. Unlike solid-state experiments, the dilution fridge not only contains the sequence of cold plates that are going down continuously to the millikelvin range, but we have repeated the 4 Kelvin plate further down again to host atomic traps. Essentially, here are electromagnets for trapping atoms in a magnet-optical trap at 4 Kelvin. As this movie illustrates, this is here inside, of course. For this, the vacuum chamber is closed. And once the atoms are trapped in the MOT, we transfer them into the magnetic trap, and using a magnetic conveyor belt, we guide them deeper into the millikelvin system, where now a flipped chip cavity, as described before, is installed and waiting us back to the lab. Now, if we explore hybrid quantum systems, combining atoms and superconductors, converting microwave to optical photons, or interfacing some other components from our quantum toolbox is many. The challenges, the scale of challenges is huge. But so the opportunity. So with this, I would like to leave you now with the encouraging words of István Széchenyi, the founder of this Academy of Sciences, who told that everything depends on us. We only need to want it. With this, I would like to thank you very much for the attention.
Thank you for this nice talk. So we have time for questions. It's a bit intimidating, this great hall, but please feel strong and stand up to raise questions. I can, there I'm.
Thanks for the beautiful talk. So my question is more technical now into the future. So for example, optical tweezers, they can shake a lot, and now that you put them close to the pulse tube, you hear it right on the audio. So have you already observed some kind of vibration of the tweezer compared to the chip, or you still plan to do these experiments, or are you afraid of that? Can you comment on this?
So thanks for this very important question. Essentially, the pulse tube is introducing vibrations. So in the design, we have taken care to minimize these vibrations. And the measurements indeed show vibrations on the micron scale. We can't avoid for the moment. The question how far we can suppress this. Now, the answer on that, if we would do the experiments again on a planar substrate, this would be a problem. However, in a flip chip geometry, when atoms are trapped between capacitor plates separated by, let's say, 100, 200 micron distance, here 150, then this vibration is to this time, the smallest contribution to the measurement error certainly needs to improve, but it would improve the proof of concept measurement significantly. Yeah. New cryostats can be designed even with further noise reduction. Yeah. Mm-hmm. Thank you. Mm-hmm.
Thanks for the talk. You partially mentioned this in this answer, but what is exactly this flip chip geometry? Can you describe it better?
So actually, these are lumped element microwave cavities ending in capacitor plates, and the capacitor plates are confining the microwave field, so in free space. So this is one of the possible cavity geometries that is compatible directly with superconducting other superconducting circuits in terms of coupling, and have at the same time very free optical access to move atoms into the setup. So it's not yet explored. The hardware is in place, and this is one of several possible cavities that should be explored in this context. Mm-hmm.
Hi. Maybe I misunderstood, but you said you choose the Rydberg atoms by the tweezers. How does that choosing work? So maybe this was not the word you used, but you said that you choose the Rydberg atoms by the optical tweezers.
We position the Rydberg atoms by optical tweezers. So first we position the atoms by optical tweezers, and then we excite them to a Rydberg state. So the optical tweezers are taking the atoms from a larger atomic cloud and position them always, or shall position them always to the same spot inside the cavity. The techniques are now widely used, optical arrays, so this is also advancing this field when coupling to solids. Once the atoms are in tweezers, we are free to choose the excitation. Certainly, we select Rydberg states that fulfill some conditions. First of all, they must match the cavity resonance. Second, we prefer Rydberg state that have the same Stark shift, or they have essentially a minimized differential Stark shift in an electric field. So even if the position varies a bit, and this is connecting also to your question, so they are Rydberg state pairs that have the same differential shift, such that a variation of stray fields do not shift to resonance. If not, microwave dressing is applied to Rydberg states to stabilize this shift. So there are several steps to adjust, and all this contributes to stable coupling to cavities. Mm-hmm.
Thank you. Just as a follow-up question on this, so you position your atoms in the tweezers, and then you excite in the Rydberg states, but depending, I think, in the rubidium atoms here, you will not trap the Rydberg states, right? So you have to release the atoms and do things in free fall. So now the question is about time constants. So what is the coupling strength you can get before the atoms spread too much and there's some broadening? Is this an issue, time constant, an issue on this?
Okay, so we expect several megahertz of the Rabi frequency, so the experiments shall be done fast. So even a release should not be a problem. Yeah. Yeah. Thank you. Mm-hmm.
So I have also a question. So you had this dilemma of choosing between the collective enhancement but you had the inhomogeneity, so this is why you turned to single atoms, where you could have a benefit of large dipole, electric dipole. But in the end, I was disappointed that there was again inhomogeneity, so you had to make further operations like this tweezer, for example. So do you completely abandon the possibility of having a solution with collective enhancement and fighting against the inhomogeneity?
Okay, now this is an oscillation back and forth, this time without damping. So we try experiments with Rydberg atoms, single atom coupling to the cavity. At the same time, we just stepped back to look at the collective coupling. So it is both, I believe both paths will leave us, will guide us to the point of coupling, and we have to pursue both. Yeah.
Okay, thank you. If there is no further question, I would like to thank the speaker again.